So our last concept when we're talking about fluid mechanics is something that we've also put to very good use for several tools, several pieces of technology we use, and that's something called Bernoulli's principle. And you've probably experienced this. If you were taking a shower in a shower with a shower curtain, I don't know if you've noticed, but when you step into the shower, that shower curtain is drawn into you. And that is because of this thing right here, because the fluid inside the shower is moving at a much faster pace than the fluid outside the shower. Outside the shower, things are just kind of normal. When you step in the shower, you've got this water shooting out of the shower head. And not only is that moving fluid that's shooting out of the shower head, moving liquid, but it's also moving gas, moving the air molecules around that liquid. So this is how it applies with Bernoulli's principle. When fluids move, their pressure changes. How? Thank you for asking. The pressure in a fluid will go down as the fluid's velocity increases. So the faster fluids are moving, the lower the pressure where they are. All right, and one really good example of how we've used this is in the concept of lift. We're going to do some activities with this. Also, our air tunnel is a good example. I'm probably going to video that and show you that again. But just to draw you a little diagram here, if we were to take a cross section of an airplane wing, all right, what's a cross section? Oh, don't make me draw it for you. Okay, but here, let me try, I guess. Okay. Oh dear, you know I'm terrible. Okay, here's an airplane, here's its wing. All right. Okay, that's a really bad airplane. All right, but, okay, cockpit. Okay, here's the wing. And when we're looking at a cross-section of it, here's what we're doing, just like in biology. I don't know if you remember that word, but we're making a cut here, okay? We're cutting the wing like that, and that is giving, and then we are looking at it as if we are facing it. We took this piece of wing, we cut this one off right here. We're taking it and we're looking at it like this, all right? If you were to do that, you would find that those airplane wings have this sort of shape. They're not just the same throughout. They have, up here, it goes up like that. Okay, that is because of Bernoulli's principle, this kind of shape creates lift. How does this kind of shape create lift? If you think about this, if our airplane is moving in this direction, okay, and our airplane is moving with a certain velocity, okay, that velocity is basically that our air molecules are traveling over this wing in this direction, relatively. Because the wing is traveling this direction, so it's as if our air molecules are moving in that direction as far as this wing is concerned. Now my question is there a difference in velocity at the top of the wing and the bottom of the wing? If you answered yes, you're correct. And the reason is simply this. What's velocity? Velocity is displacement over time, right? And displacement is a length or a distance, okay? This has a certain length right here. If we were to take this and stretch it out straight, would this length be longer, shorter, or the same as this length? If we were to take this length right here and flatten it out straight, how would it compare? If you answered that the top of the wing would be longer than the bottom of the wing. You answered correctly. All right, so we have a certain velocity here on the blue part, on the bottom of the wing. There's a certain amount of displacement that's happening per time on the bottom of the wing. How does that displacement compare to the top of the wing, the red part? Well, it has to be bigger, right? All right, there's bigger displacement per unit time on the top than the bottom. And obviously that has to be true because the top part of the wing doesn't arrive somewhere before the bottom part of the wing, right? Okay, the wing gets to where it's going at the same time, both sections of it. Which automatically means that the top part has to be having a higher velocity of air molecules flowing over it than the bottom part, okay? And what did Bernoulli's principle say? It said that the higher the velocity of the fluid, the lower the pressure. So if we have higher velocity on the top, okay, lower velocity on the bottom, what does Bernoulli's principle say will happen? It says we will have lower pressure on the top and higher pressure on the bottom. What does that give us? That gives us a situation of something called lift. Okay? We have lower pressure here, which basically, and it's intuitive if you think about it, there are fewer air molecules on the top of this wing because those air molecules are moving faster over there. Okay, so there is less pushing down on the top of the wing. What does the top of the wing want to do? If there is less pushing down on it, less pressure pushing down, well, it wants to go up. And with our bottom part here, it has a lower velocity, which means it has to have higher pressure, but which way is that pressure going? It's going up. So what we get is this thing called lift, and it's used in many situations, many shapes of, airfoils on cars. It's all about creating a situation where this object wants to move up, and that's lift. Bernoulli's principle.